So in this video, I plan to go through the simulation design flow. So this is really useful if you want to design an FFT to go on an FPGA, but you don't have an actual development board to work with. So you're not able to use signal tap. Now, if you've seen my previous video on the spectrum analyzer, you'll see how convenient it is to have something like signal tap for debugging. But the second best thing is to simulate, and it is very possible to simulate a whole design, even with FFTs. But you do run into a problem, and the big problem is, what do you use to actually feed the FFT with? What signal do you use? And the way I've overcome this problem in the past is to use a numerically controlled oscillator, which will give you a sine wave at practically any frequency that you ask for within its limits. So in this video, that's what I'll go through. I'll go through the design flow to simulate an FFT using the NCO as the stimulus. So let's see how to do it. So I'll start a new project, and I will choose a dedicated folder for my new project, Simulating FFT, and I'll give the project a name, just a short descriptive name. So it doesn't matter so much here that we select the correct board, because we don't really intend to program any device. So I'll just leave it as the default here. But if you do go on to programming an actual FPGA, you have to make sure you have selected the right one here, otherwise it won't work. So I'll just leave that. So simulation, I'm going to use ModalSim Altera and Verilog HDL, and that's it. So that should start a new project for us, and the first thing I will do is go to File, New, Verilog HDL file, and I'll start writing my testbench. So we have the timescale precision command here, so I'll go for 10 nanoseconds timescale and 100 picoseconds precision. I'll call this module testbench, and I know I'll need a clock, so I'll just declare a register clock, and I'll initialize it to a starting value of 0. And just make sure I have begin. So that really is the skeleton of the testbench. What I want to do now is just generate my FFT. Then I'll write a wrapper for my FFT. What I'll do is actually use some code that I developed in the previous video. So if you haven't seen that video yet, just go back to that one. I wrote an FFT wrapper that deals with all the interface circuitry that you need, especially the start of packet and the end of packet signals and all of the other control circuitry. I'm not going to rewrite this in this video. But I do need to generate the FFT. So I'll go to the IP catalog, search for FFT, and then go to the IP parameter editor. So this will pop up. Just drag it across here. I think I'll stick with a 1024 point FFT. The direction I'll stick with bidirectional. That means you can perform a forward FFT and an inverse FFT. Even though I have no intention of using the inverse FFT, it seems to be that the bidirectional FFT seems to be a bit more easier to set up. I'll go for variable streaming, and I'll go for natural output order. Now, my data input width, that's the width of the data going into the FFT, I'll make that 14 bits so it is consistent with my other projects. And the output width I will set to the maximum of the output range, which is 25 bits. You can see here that we have a throughput latency of 2048 cycles. So that means it will take 2048 cycles for the FFT result to come out of the FFT compared to when you put it in. So I think that's finished. So I'll just generate HDL, and you have to make sure here that you have a simulation model. So you can see here the default is none. If you don't select a simulation model here, you can't simulate it in Model Sim later on. So that's really important that you make sure to remember to select Verilog, or if you're using VHDL, select that one. But in this case, I'm using Verilog, and that will give me a simulation model that can be used by Model Sim later on. So I'll hit generate. So that will start the process of making this FFT. Once that's done, that should appear in my project navigator. Okay, so this is actually an important step. So it makes you move the .quip and .zip files into the project folder manually. So I think it's the next pop-up. So the one that's important to us here is the .zip, because that's the simulation file. So we have to make sure that we go to add remove files in project. This is the folder we just created, FFT, into simulation. And you can see the .zip file is not there by default, but if you go to all files, you can see it appears. And we just have to make sure that is put into our main project folder. So I'll hit apply. Okay, so now you'll notice that we have the fft.zip in the project navigator, and we also have the, well, it should be here. This is because I haven't done the .quip. So I'll just make sure I do this properly. So I'll go back to FFT, synthesis, and I'll make sure that the .quip file is also in my folder. And you can see now in IP components, the FFT mega function is in the project navigator. And that's quite convenient, because if you want to change this mega function later on, all you need to do is go into IP components, double click this, and the IP parameter editor will open up again, and you can regenerate as necessary. So that's a good thing to remember. But now we have the FFT generated, that means we can now instantiate this into our design. And as I said before, I've already written a wrapper for this purpose. So I'm just going to copy and paste this across. So I just need a new Verilog HDL file, and I'll just paste that code into here. So you can see this module is called FFT wrapper. It basically instantiates the control module. That's the one that's producing the start of packet and end of packet, and the sync valid and the sync ready signals which the FFT needs. I also instantiate here the FFT itself, which should be okay because we've now created that within Quartus. So that is the wrapper. I'll just save this as FFT wrapper. And I'll just make sure as well that we also bring this module over from the other project. So I need a new Verilog HDL file, and I'll just make sure that the control circuitry module is also brought over, because that is instantiated in the wrapper. So we also need that to be in our project navigator. So control for FFT. So I'll just save this as control for FFT. If we look at the FFT wrapper again, this is the control module. That's control for FFT.v here. The FFT is from the mega function that we just created, and the FFT wrapper is also saved in the project navigator as FFT wrapper.v. So we should have everything we need here to make a start. So the next thing I plan to do here is instantiate this FFT wrapper module within our test bench. And I showed you in the last video, there's a shortcut you can take here just to save on some typing. So if you right click the FFT wrapper, you can create a Verilog instantiation template for current file. So let's just save test bench, and now it should make a instantiation template for the FFT wrapper, which we can open, and it is, and then we can copy and paste this into our test bench. And you can see it's done most of the work for us here. It's instantiated the module within the test bench. It's done the dots and the brackets. We just have to make sure that the default names that it's given us here are abided by when we write our other code in the test bench. But yeah, that's a time-saving tip. We have our FFT wrapper instantiated. That's got our FFT inside. So what we want to do is inject a signal into this port, and that will go into the FFT, and the FFT will be carried out, and then we'll see what the FFT results are based on the output signals here, which are real power and imaginary power. But we have a problem here when we simulate, because there's no easy way or obvious way to generate some kind of input signal. Now, ideally, what we would want is maybe some kind of sinusoidal wave, or maybe a more complex signal where we have a combination of sinusoidal waves at different frequencies. Well, the closest thing we can get to this in simulation is to use what's known as a numerically controlled oscillator. So I'm going to search for NCO here. So it's under DSP and signal generation. And I'm just going to double click this and open up the parameter editor so we can take a closer look at what the NCO actually is. So an NCO is basically a way to generate a digital sinusoidal wave. So if I go to time domain here, you can see this is a replica of the sinusoidal wave that would be generated by this NCO. And the good thing about NCOs is we can change the output frequency. And the way that we do this is by changing the input value to the phase increment port of the NCO. You can see here the default values. It thinks that it is getting a 100 megahertz clock, and it's giving us a 1 megahertz sine wave. And it's telling us here that to get that, we would need to input this number to the phase increment value port. Now let's say we wanted 2 megahertz. You can see that number changes. And even when we generate the NCO and put it into our design, we can actually change this number at any time. And you can do all kinds of other things like frequency modulation and complex waveform generation. One word of caution here is, let's say we had a 40 megahertz clock, which is the one we're actually working with here. Then you wanted a 15 megahertz sine wave. You can see it gets very blocky, and that's because our sampling rate isn't really good enough to get us a 15 megahertz sine wave. So the number I'm going to go with here is actually the one that we worked out in the previous video, the one that falls exactly on bin 10 of the FFT result. And if my memory serves me correctly, I think it's 390.625 kilohertz. So it would be 0.390625 megahertz. This is the phase increment value that would be required to give us that frequency. So I'm going to copy that number, and I know then that that's going to be the number that we have to input into this NCO to give us this output frequency. And that is a really nice input for our FFT. So magnitude resolution, I'm going to choose 14. That's the input resolution of our FFT. And I'm going to leave everything else the same. So I'm just going to generate HDL. Again, let's make sure that we have a simulation model here. So we have it set to Verilog. That's good. Now we can use it to do a simulation in Model Sim. Everything else is correct, so I'll hit generate. Once that has finished, we can then go ahead and hit finish. So close, finish, and again, Quartus makes us do some extra work here in terms of moving the .quip and the .zip files into the project folder. It'd be good if there was a button that could do this automatically. So NCO, so we need to go to simulation, all files, and let's get the .zip into the project folder, and then we can do the same thing for synthesis. And then we can see in IP components we have the NCO mega function, and if we want to edit this or change it later on, we just need to double click this, and that will take us back into the IP parameter editor and allow us to edit that component. So what we need to do now is instantiate the NCO within our test bench here. The way that I do this is another shortcut. If I go into the .quip here and select NCO.v, it actually gives us kind of a template here that we can copy and paste into our test bench. We do have to change this name. That's not the proper name for the NCO. So let's just change it to NCO and then NCO inst. You can see I'll just change the FFT clock to clock, but you can see here that everything else is correct. We just need to generate the sine and the cos outputs from the NCO. And I'll just change the reset signal. So if you watched the previous video, you would have seen that we generate a reset signal from within this FFT wrapper. So it starts off at 0, and then after a count of 10, it goes to 1. So what I've done is exported that reset signal, and I'll export it from the FFT wrapper, and I'll use it for the NCO reset signal as well. So I'll just make sure that I have a wire called reset N, just to act as a connection between the FFT wrapper and the NCO. That should be okay. We just need to generate the wires for the sinusoidal and cosine outputs of the NCO. I'll just connect the sinusoidal output to the input of the wrapper, like so, and then just make sure that we have these signals declared within our test bench. So it's going to be sine and cos. It's the same signal, it's just 90 degrees out of phase. The other thing I'll do is just change clock enable on the NCO to 1, just hardwire to 1. And then we need to change this phase increment value. So this is a 32-bit number. And I did copy from the NCO mega function, but I've noticed I've just overwritten that with another copy and paste. So I'll just go back into IP components. I'll open the NCO again, and I'll just retrieve the phase increment value that will give us the frequency that we want. So here we are again, go to frequency, copy, close this, and then just paste that in. And then end module. So that is probably okay. I'm just checking to see if there's anything I've missed. One thing I have missed is the clock generation. So to make a clock, we need to put inside an always block, we need to use the hash command just to delay the signal and then invert the clock. So that will give us every 10 timescale units, it will invert the value of clock, and then that will look like a square wave, which will be used for our clock. So I think that's okay. So I'll go to the next step now, which is to set up the test bench within Quartus. So I will make sure that the test bench is the top level entity. Then I will go to project. I'll go to assignments, settings, EDA tool settings, simulation. And then we need to make sure that Quartus knows that we have a test bench that we want to simulate. So we just have to make sure that the name of the test bench that we put in here matches the module name of our test bench. And then we need to find the actual .v file for our test bench. And then add it, okay, apply, and then Quartus knows that we have a test bench to run. Next step, we can go to start and then analysis and elaboration. Very common to get errors at this point. This time we've escaped with no errors. Let's see if we can open Model Sim. So as soon as you've finished analysis and elaboration with the test bench as your top level entity, we can then open Model Sim. If you do try to go to Tools, Run Simulation Tool, RTL, Simulation, and then you get an error message, it's probably because you haven't linked up Model Sim with Quartus. And to do that, you need to go to Tools, Options, EDA Tool Options, and you need to change the path for the simulation tool that you're using. This is the path for Model Sim Altera. Let's go to Tools, Run Simulation Tool, RTL, Simulation, and it is actually common to get some errors picked up by Model Sim that weren't picked up in the analysis and elaboration. And they tend to be very difficult to diagnose and solve once you get to Model Sim. So fingers crossed. So Model Sim will open and it will process the simulation. I've just detached the wave window here just to make it easier to see the waveforms when the simulation starts running. Just make this a bit smaller. So the simulation is running. So I'll just right click and select zoom full. Now the simulation does take a fair amount of time depending on the processor that you have. We can already see that we have an output for the sine and the cos outputs of the NCO. So what we can do is actually right click them, go to format, and then analog automatic, and you can see we have a nice sine wave there. So that's a very nice feature of Model Sim. You can actually plot these waveforms. Now the thing we're watching out for here is actually the output of the FFT. And you can see we've already got the sync start of packet there. So our FFT should start processing the frame at this point. So I'll hit zoom full again. We know we're going to have a latency period because it takes some time for the FFT to process and start outputting the results. It looks like we have something. So I think what I'll do now is just go to simulate and break, just to stop the simulation and just make it easier for us to have a look at what we have. Again, what I'll do is right click, go to format, okay. So that there is actually a mistake here. So real power and imaginary power, they're 1-bit signals here. So we have to go back. Okay, this is a common kind of error. So we had a problem in our code. So if we go back to the test bench, we can see that these two signals, we have not declared them as 25 bits. We've declared them as, well, we've left it as the default here, and Model Sim will take these as 1-bit signals. So we just need to change those to 25-bit wires for the real and the imaginary. Okay, and then go through the process again. So we save, analysis and elaboration, and then I'll come back when we get back to Model Sim. So here we are back in Model Sim. So now we have 25-bit signals for the output of the FFT, so that should capture the true output of the FFT. So we're just waiting for those signals to come out. Keep hitting zoom full. So there we go. So the signal is starting to come out of the FFT. So I'll right click and I'll go to format, analog automatic, and I'll do the same thing for the imaginary output. And you can see that we have a spike. So I'll just zoom in on the cursor here, and if this is the start of packet, so you can see, you know, around about bin 10 we have the spike, and that's exactly what we expected. We'll just let it run a bit and we see the same thing repeated. So that spike corresponds to the 390 kilohertz signal. This, we can say, is working as it should be. So this is quite good if you don't have a board, if you don't have an actual FPGA development board, you're not able to use signal tap. This is probably the second best thing you can do. So you can build up your code, you can develop things, you can simulate in Model Sim, and you can still get a good idea that the code is doing what it should be doing. So I hope that was useful. Thank you for watching, and I'll see you in the next video.